anyways, after this, you're going to be able to solve explosion and collision problems in 2 dimensions. I will tell you this, on the test, there will be only one 2-dimensional question. It will either be explosion or collision. I think there's been some years where I've put 2 questions and you get to pick. Do you want that, or do you want me just to randomly flip a coin and pick one of those 2? Pick one? Okay. Okay, so it'll be something like this, where you've got mass 1 colliding with mass 2, and they sort of go off to the side. Now that obviously makes me think about curling, so I went looking for the physics of curling, and this is what I found. And I've got a little question mark here, Santa Clara University question mark, which you'll understand once you see the video. The university professor at Santa Clara University down in California decided to make a video, so it's kind of amusing to us Canadians. Okay. How much room do you guys have? You're right at the top there, right? Okay, so it's going to be like the entire page. If you're a big writer, you might want to do it on loop. It's up to you. Okay, I kind of have unlimited space here. So. All right, so 2 identical curling stones of mass 19.5 kilograms collide, as shown. The first stone hits the stationary second stone with a velocity of 5 meters per second north. If the velocity of the first stone is 3.2 meters per second north 30 west after collision, find the velocity of the second stone after the collision. Omit friction. Okay, so do you think a picture is probably a good idea to start with? Just to sort of get a handle on, and a little pun there, a little handle on the situation, right? So we've got one is stationary. I'm going to try to remember to do them in different colors. So there's the red one, and the blue one is coming like this, and they are identical. Okay, if you want to label them A and B or something like that, you can.
Just do R and B.
Sure. Okay, and maybe what I should do, the first stone, so let's change this to blue, and change that to blue, and the second stone is the red one, right? So afterwards, the velocity of the blue stone is 3.2 at north 30 west. So afterwards, north 30 west, the blue one's doing this. Yes, Carter? Thanks. So the question is, which way does the red one go? Well, we all know, we've at least seen curling on TV. We all know that the red one's going to go which way? That way. Now, is it going to be exactly 30 degrees?
No.
You kind of get the feeling, well, maybe it should be, but you've seen enough curling to know that that's probably not the case, though, right? Probably. So we'll have to check that out. Okay. So will we agree that the initial momentum is equal to the final momentum? I think we've established that now, that momentum is conserved. So what this means is in 2 dimensions is really Pix is equal to Pfx, and Piy is equal to Pfy, right? The y momentums have to match before and after, and the x momentums have to match before and after. So really, all you're doing is you're doing conservation momentum in 1 dimension, but you're going to do it twice, exactly, for the x's and for the y's. And if you keep that in mind, again, I keep coming back to this, it's the setup, it's the notation, it's how do I write it down that makes it work. But if you know that thought, like, I don't care if your notation matches mine, I'll figure it out. And in all honesty, these are extremely challenging to mark, okay? Because everyone's kind of got their own setup. It's kind of complicated. I'll admit right now, I looked at the bottom number, and if it's right and the work is there, you're getting full marks. Okay? Having said that, if it's not right, guess what I have to do? I literally have to go through line by line by line. This test takes me forever to mark. Okay? And obviously, the more work you show, the better chance you have of getting some marks, because, like I said before, sell me on the fact that you know something. Okay, so, I always think, I'm going to do this one in a vector subtraction sort of format. Okay, so the initial momentum here is made up of what? Momentum of B, right? fact, I'm going to do this just to make it. Make a little more sense visually. And the final momentum is made up of what? Why did I not include A there, or the R one? Because it's at rest, exactly. Okay, because it's at rest. So the final momentum is made up of PB prime plus PR prime, and I've switched over to this prime notation instead of the I and the F, right? Okay, now what are we trying to solve here? We're trying to find the velocity of the second stone after the collision. This is the red one. We're trying to find a part of that guy there, right? Yeah? Okay, so could I take this PB prime to the other side and make it negative? Would that work? Could I say that PB minus PB prime is equal to PR prime? Does that make sense? I just took this value here, went to the other side and made it negative, right? Now, are these vectors? Absolutely. Momentum is a vector. I mean, technically, we should have the little vector symbol across there. That complicates things. It makes it look complicated. But really, we are talking literally here about vector subtraction. Have I taught you vector subtraction already? Absolutely, right? This is a redo of vector subtraction. So when you're, talking about redos, here's your chance. Okay, so let's break down momentum B and PB and PB prime into vector components. So PB is actually this one here, right? It's not the prime, so it's going to be, now we figured out the momentums yet? All I have is the masses and the speeds, right? So this is really going to be mass of B times velocity B times mass of B times velocity B prime is going to equal our PR prime. So that's going to be 19.5 times 5 minus 19.5, and the velocity of B prime after is 3.2 is equal to PR prime. 19.5 times 5 is 97.5. And 19.5 times 3.2 is 62.4. Now, are those numerical values? No, they are vectors, so they need that direction. So north, and this one here is north 30 west, is equal to PR. Okay, so again, we're doing vector subtraction. So now that I've boiled it down to that, we're going to sort of arithmetic mode here, and I just have to do vector subtraction. So 97.5. This is PBX and PBY. I've got to break it into components. That's how we do vector subtraction, right? Break it into components. We're fortunate in that there is no x component for PB. It's 0. What is PBY? 97.5. Now we do the same thing with PBX prime and PBY prime. And it's going to be 30 degrees, and this value here is 62.4. The x is opposite, so that's going to be 62.4 sine 30. I get 31.2. I would mind if someone confirmed that for me. And the PBY prime is going to be 62.4 cosine 30, or 54. Anyone see any issues up to there? I've purposely made a mistake. X should be negative. Why is the X negative? Because it's going to the left. Exactly. Okay? But I knew that it was a simple one we could solve. I put that in there. Okay. Now, we've already established that we're doing vector subtraction, so we're going to take this value here, subtract this one. So really, we can show like subtraction, right? That's what we're doing. We're doing this, subtract that. And what is that going to equal? It's going to equal our momentum of the redstone after the collision, which we will label here PRX prime, I guess, because it's after collision, is going to equal 0 minus 31.2, which is just 31.2. And PRY prime is going to be 97.5 minus 54. I get 43.5. Okay. Both positive, is that right?
Yeah.
Does that make sense? The red components are to the right, the X is to the right and the Y is to the up. Yeah, that's what's happening, right? Have you guys run out of room yet on your page? Good. Okay, so now how do I get going back to my answer here? What am I going to do? Vector subtraction? Put them back together again, right? So I'm going to take my X and my Y and I'm going to put them back together. So I'm going to draw them, showing my work, 31.2 and 43.5. And so this value here will be the momentum of the redstone after the collision. So P, R, prime, that's supposed to be a bracket. P, R, prime, squared is going to be 43.5 squared plus 31.2 squared, and you get PR prime. You guys can do that Pythagoras. You've been doing it for years. 53.5 kilogram meters per second. That is the momentum of the redstone after collision. 53.5. Say again? We do. Because let's look back and actually see what the question says. The question says, find the velocity of the second stone, right? So what do I have to do? I not only need the angle. Should we do the angle now? We got to do it eventually. Yep. Opposite over adjacent. 43.5 over 31.2. I get an angle of, and I did it the other way on my page here, 36. You're going to get 54. Did you get 54? Yeah, sure. Okay, so that's going to be, according to this diagram, that's going to be east 54 north. That's the direction, but we want the velocity, so P equals mv, and I purposely put that space over there because we kind of like having the velocity over on the left. So the momentum is this value here of 53.5. The mass, I think, was 19.5. We're solving for the velocity, and you get 2.7 meters per second. Does this feel reasonable?
Yes.
The angle is east 54 north, which seems about right? And 2.7 meters per second, well, what was the speed of the other one? It was going at 5, and then the other one goes at 3.2, 3.2 and 2.7, yeah, that's right in that ballpark, right? Is that a hard question? Absolutely. I get it. That's it. Oh, well, that's a good thing. Yes, Dan. Oh. Should I go through it again, sort of like the steps that we did? No? I will, I think, anyways. It's probably good for us. Okay, I'll wait. Okay, so let's go through what the steps were. Okay? And I have to be honest, some of this stuff at the start was me getting my head into the space. I know last semester when I taught this, I'd just come back from the old crack in the noggin, and this was probably the worst lesson I taught. And I went home and I felt terrible because this is hard stuff. I actually feel pretty good about this today. I think I've done a pretty decent job. Mainly because I did this stuff at the start and I sort of got my head into the idea of, I was trying to show you that I was trying to really think out loud, really, how to work this through. Okay, so start with PI equals PF, that's that good framework structure, right? And then I think I said, went to this, right? And you probably got mad at me because I moved this over. So the X components have to add up to the final X components and the Y components have to add up to the final Y components. And then I decided to do it by vector subtraction. So I said that the initial momentum is made up of only the blue stone, right? And the final momentum is made up of the blue stone plus the red stone. And then I realized I could do vector subtraction here. So I took the PB prime to the other side, and I got that the PR prime, the red stone's momentum after collision, is equal to the momentum of the blue stone minus the momentum of the blue stone after. Okay, and then we figured out those momentum values, and I boiled it down to vector subtraction. We broke it into components. We know it's vector subtraction, so we subtracted. We got our redstone components after, and then we combined them together using Pythagoras, and we found the angle, and then we found the speed. Is that the only way to do that? No, it's not. Is it a good way to do it? I don't know. It's a good review of vector subtraction. Anybody want to ask me anything? Alrighty, so this one is a 2D explosion. We got a 5 kilogram bomb, it's at rest, it's exploding into 3 pieces, each of which travels parallel to the ground. The first piece with a mass of 1.2 travels at 5.5 at an angle of 20 south of east, and the second is a mass of 2.5, travels at 4.1, and blah, 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 blah. Determine the velocity of the third piece.
The third piece would be another curveball.
You think so?
Yeah.
I guess. I mean, 2 pieces would certainly be easier, you're right.
Use that another trunk in there for some extra X and Y.
Well, we'll do this. It's not that bad. I'll show you. It's not that bad. Okay, so the first piece with a mass, I'm going to draw, there's the before, it's at rest, right? Which tells us that the initial momentum is 0. Okay, that's awesome, because that means that the whole left side is 0, right? So that's awesome. The first piece with a mass of 1.2 travels at 5.5 at an angle of 20 degrees south of east. South of east. East, there's east, so south of east. So that's 20 degrees. That's piece 1. Do A? Okay. I agree. The second piece is a mass of 2.5, it travels at 4.1 at an angle of 25 north of east. North of east. East. So you have to kind of take your time and sort of read carefully and just, you do, right? Okay, which way is the third piece going to go? Kind of that away, right? I got an A in red down here and a B in there. So piece C is kind of going to go like, is this not really equilibrium in forces kind of idea? They all of these vectors have to add up to 0, right?
But is E 25 degrees?
Here's 25, yeah.
You just add A and B and then just put like that.
I guess you could, yeah. Dan is suggesting that we take A and B and just add them together, right? right? He's saying, let's take those two and add them together and find the equilibrium of that, which would be kind of like equilibrium momentum. I don't mind that. That's not what this sheet says, but do you want to try it? I think I like that, actually.
Can you do that for every single one?
I'll maybe have 3.
Hey, I'll give you the easiest part of the question. What's that? You can all do this. The mass of the third piece. If you can't do this,
2.5.
you really can't do physics. I'm sorry to say. It's going to be 5 minus 1.2 minus 2.5, which is 1.3. Mass of the third piece is 1.3. Because
Do A, B, and 3?
How do you figure that? You take the total and you minus the 2 chunks that you have.
third piece. C. Good pick, Joel. Good catch. Yeah, you're right. Notation's got to be the same. I had it here as 3. That's going to cause me some grief as I'm doing this here. Okay, so we know that the x's and the y's have to add up to 0. So I'm going to say, in fact, Carter's going to get mad. I'm going to be in trouble here. Well, I don't have to get, no, we'll do it this way. Can I just go this, Carter? Will that be okay?
Yeah.
That's fine? Okay, so that means that the final x components have to add up to 0. So in other words, momentum of ax plus momentum of bx plus momentum of cx. And do I need to do the prime thing?
Sure.
You can if you want, but there's no before collision because it's an explosion, so it's 0, right? So that's just cluttering things up. Okay, so, yeah, I have to find what the momentum of AX is. This is A, X is there, so it's going to be that mass of A, which is 1.2, times the velocity of 5.5, and it's going to be adjacent to that 20, so that's going to be cosine 20.
What?
Yeah, I'm not happy with this.
Well, you forgot to do that.
I,
MA.
yeah.
You forgot to do that stuff.
Okay,
So just slide that down.
slide that down? Okay. I also think,
You need to add formulas in here, because I don't know.
okay, yeah. Here's what I'm going to do. Hopefully you're working on a pencil. Okay, there's my description. So now what I'm going to do is I'm going to draw out, this is piece A, right, which is going at 20 degrees. And the momentum of A is the mass of A times the velocity A. Sorry, no potatoes today. Yeah. Unless it's like an exploding. Maybe it could be, I should say that it's a 5 kilogram exploding potato. What was the mass of A? 1.2. 1.2, and the velocity of A is 5.5. $6.6. Carter's not going to like this. Apparently I made everything one tiny little. B is 25. And momentum of B is mass of B times velocity B. And that is piece 2.5. The velocity of it is 0.1. .25. Okay, so what was that step there, Hannah? What did I do? All I did was find the momentums of those two pieces, right? but I have not yet broken them into components.
So what is this value? This is like where they're actually going.
This is their momentum, we just haven't included the direction, right? So now I need to find the x and y components for those. So PAX, which is this guy here, is going to be 6.6 times cosine 20. $6.2. And should I do the y on the right hand side?
It doesn't need to get.
Underneath? Yeah, I kind of feel like underneath better. .26. Maybe I'll be consistent and go 3 decimal or 2 decimal, 1 decimal. It's 2.3. Okay. Direction. Right and down. So that means the y is down. Are there a lot of places to make mistakes here? Yeah. Are you glad you don't have to mark these? PB, I guess I kind of did these in the wrong color. PBX is going to be 10 point, oh, I can do it like that. 10.25 times the x here is adjacent, so that's going to be cosine 25. 10.25 times cosine 25. 9.3, we'll say. And PBY. 10.25 times the sine of 25. I'm not going to disagree with you, whoever said that. Okay, directions. Right and up. Positive. Okay, so I've got it broken into components. Let's go back here a little bit. What do I have to do now? I'm really trying to find this here, right? I'm trying to find the C components, both x and y. Sorry, Carter. I can get rid of that one. Because I'm also going to say 0 is equal to PAY plus PBY plus PCY, really, right? So we're going to do the same thing for both of these. So how do I find the C? Well, 0 is equal to PAX plus PBX plus PCX, and now I know those x components. So 0 equals, and I now see what I need to do, 6.2. I'm going to add the B plus 9.3, and I don't know PCX. That's what I need to find. Does that make sense? Jesse, yeah? Okay. So PCX, those are going to go to the other side, and it's going to be minus 6.2 minus 9.3, and I think you get, I'm going to have to do that here because my 15.5. In fact, that's going to be negative. And does that make sense that it's negative? It does, because we know it's got to go left, right? Okay. So what do we do with the y's? Do we do the exact same thing with the y's? We sure do. PAY plus PBY plus PCY. Yeah? What about brain? Is brain cramping? Brandon just gave me a little nod. He was too afraid to shake it too much because it might sprain his brain. PAY is this guy here, minus 2.3 plus 4.3 plus PCY. So PCY is going to be 2.3 to the other side minus 4.3, and it's minus 2, which kind of makes sense. It should be left and down, right? The piece that, okay. Do you get the feeling we're close to done here? What do I have to do now? I've got the x and y components of the third piece, so what do? Put them together, right? Again, back to vector subtraction. It's the same process again. So minus 15.5 is this way, and minus 2, I guess, is much shorter than that, isn't it? So minus 2 and 15.5. And so momentum of piece C squared is equal to 15.5 squared plus 2 squared. I guess it's negative. Does it matter if they're negative? No. It doesn't. The momentum of C is going to be 15.5 squared plus 2 squared equals, don't forget to take the square root, 15.5 squared plus 2 squared equals square root 15.6. That seems to me to be pretty reasonable. And that's a unit of kilogram meters per second. It's momentum. Could I show this to the grade 11s this afternoon to scare them? Okay, last step. What am I actually having to find? The velocity of the third piece. So I got to convert momentum to velocity. How do I do that? P equals mv. Yeah, oh yeah, we're going to find the angle. 15.6, what was the mass that we worked out? 1.3? 1.3 v, so the velocity of the third piece is 15.6 divided by 1.3, which is 12. Is that a ballpark reasonable figure? 5.5 meters per second, 4.1. This seems kind of high. But is this the smallest piece? Yeah. Okay, so we're good there. So now find our angle here.
No, it's not the smallest.
Oh, it's the second smallest piece? But do the directions matter with the size of it? Yes, it does, right? So at least it's in the same ballpark. Right? Like the other ones are 4.1, 5.5, 12. Okay, it seems a little high, but it's not like 147, right? Okay, so the angle is going to be inverse tan opposite over adjacent, so 2 over 15.5, and you get an angle of, I get 7.6 or 8 degrees, and that's going to be west 8 south. West 8 south. Dan's pleased with himself because I think he did it the other way. So I kind of said it was going to be that way, but it's actually down, isn't it? Seems it-ish, right? Is that what you got? Did you do it your way?
Yeah.
If you want to jot those down just now, so there's 4 questions on page 301. And on page 302, there's a little article about police analysis of car accidents. And here's some questions as well. You know what? I ran across some solutions. Would you like me to copy solutions to these page 301 ones that I've done? Would you like those? Or should I just post them? Post them? Or should I do both? I'll make a few copies for some people, and if you want them just electronically, they'll be posted. Who wants a paper copy? 1, 2, 3, 4. Okay, I'll go make some. Why don't you find a partner and see if you can figure out this question?
Why don't you go back?
Okay.
Oh my god.
Okay. So I know that your first thought is, okay, I'm just going to take a break here, right? But I really think if you spend a few minutes trying this question with a partner, I think that would really solidify what we learned today. Pardon me?
Sorry.
You probably really don't want to.
Ironically, you're using 2D conservation momentum. Is that on purpose or just coincidence?
No, it's just on purpose.
Oh, it's just on purpose. Give that one a whirl, you guys. Think that will help you. 2 1,000-kilogram cars, and they crash together. Okay, I'm gonna go make some coffee. Just put it right there. Yes, yes.
I have a question.
Okay.
Oh,